the series. We expect to get to a point where we are very practical, but it was not possible for us to be hands-on on the first session. Introduction was very important first, but in coming sessions, I will encourage people to have laptops because you're going to build. Yeah. So, yep. Yeah. So we've all interacted with programming at some point. We've written code, and if we look at code, it's a set of instructions, and although it's one of the core activities that we do in Contuti, and there have been leaky sustained understanding around its nature, and there have been something is resonating around it, and a question of is it mathematics, is it engineering, is it science, is it art? So we need to demystify that and look at programming from all these angles, and then we're going to map it to a real world because we live in a world that has problems, and through solving problems, would come up with products, and these products generate revenue, and that's a whole ecosystem. So before you start any project or before you write your first line of code, most of the time in the spells career, thinking, we spend most of your time writing code, coming up with syntax, learning loops, event loops, syntax to be the how to compose a program, but that's just syntax at the end of the day. So most engineering begins with syntax, loops, and functions. These are essential, but that is not the beginning. The beginning is understanding why are you doing it in the first place? Why are you writing code? Why are you learning JavaScript? Why are you learning Python? Why are you learning TypeScript? So maybe how many of us are conversant with JavaScript? Just by a show of hands. Python, TypeScript, Rust, C++. So what do we deal at? Why do we learn code? Why do we write it? So we need to understand that first. So, and the best place to start with is what is a software program really? So we're going to dissect into what software program comprises of. We're going to look at the anatomy of software engineering itself, and then need to map it from what we have in theory, what we see on the platforms that we learn with, to what it actually means in real life when we're building a system. And we just go to the next one. So let us think of a program as a representation of something in the real world, like an abstract thing. Think of it as an musical score. Think of it as a legal statute that governs how operations behave. Think of it as a mathematical function that is being mapped from inputs to outputs. We'll have gone through what a computer really means. It's something that takes in input of both and output. So we will look at it also as a machine, a mechanical artifact with powers. Most of the time you can have, we've interacted with operations that require hardware that does the actual stuff. So we need to look at it from that angle. But I want us to start at this point. Programs as abstract objects. So an abstract object is not something that you can see in the real life or touch. It's like a number 7. So I can say 7 cows, I can say 7 chairs, 7 people. I'm referring to different real objects, but I'm using 7. So what is 7 in this scenario? It's an abstract object. So we can view a computer program as an abstract object that represents the physical world. Think of it, think of any software or solution out there, it's been represented by some lines of code. So it can be discovered, not invented. So these parts of some theory that we can look at it as programs as abstract objects. We can look at them also as concrete artifacts. So a program is a physical thing. a particular arrangement of bits. When you delete it, it doesn't exist anymore. So this is a materialistic view, popular among systems programmers. So we started with abstract objects. Some people view it as abstract objects. Others would view it as concrete artifacts. And then finally, some of them will view it as a social construct. So on this day, everyone exists within a community of practice. It means something because we agree on what it means. A very good example is blockchain. And you will look at some unity contracts that governs a decentralized organization, the ones that work with the blockchain, based on what the community constructs agrees with. That's what the program leads to them. Another good example is we can come up with a coin, and as a community, yes, it's a representation in bits inside our computer. We can say I have we can create maybe something called Sprint coin in blockchain. That's just code. It's a program. It's in a machine. And we can agree that one Sprint coin represents $100 in the real world. And if Joe has 20 Sprint coins, then Joe has $2,000. So that is a social construct. But it's also being represented in a software program. And in the world that we live in, mostly we look at most of fintech, we'll find that correlation there. Let's look at it now in code standard, in code format. So the first line of code there is a function written from a mathematical perspective. So you have a variable there that takes in two numbers and then gives an output of A plus B. So the output is the total of that. So that's a pure function, meaning that a pure function does not affect any other part of your program. Think of your code, think of it this way. You have a very big code base, but sometimes some parts of code affect other parts of code. And you can have a function that does not affect other parts of code. That's what a pure function really means. So I'm sure we've seen that somewhere in a piece of code. And also you can view it as a state mutation. It's a similar operation that we're doing up there, but we're now modifying a certain variable. So we are taking total, putting here in it, and then incrementing the total, and it's changing the state of that variable. It might sound so technical, but I'm sure by the end of this, we're going to go back to this slide, and it's going to be clearer. And finally, the social construct, what it means based on your context. So that is just a pretty direct definition. And let's go to the main function of this. We all are working on certain solutions in the industry, be it in e-commerce, be it a website, be it an automation, be it a digitization process that you're doing for oil company. You are applying some principles of software engineering. But let's look at it from a broken down version. So if you ask me about software engineering, this is where I can divide it into these old parts. And we're going to discuss every part, map it to real life, and associate it with technologies that we already use right now. So starting at the top right corner, that is your left, computation. We all know what computation is. We're transforming some inputs to get an output. So they give you two numbers, 5 and 5, and I tell you to add. What do you get as the result? Let me just use different numbers. If they give you two numbers, 5 and gray, and I tell you to add these two numbers, you're going to give me a result of 8. How did you arrive to 8? What did you do? You added, right? If they tell you to give me, if they tell you to subtract, well, let's do something different. And that is what computation really means. But there are questions that govern the entire aspect of coming up with a program. So one is computation. What type of operation are we doing? T is type. So type classifies values and constraints operations. The best example to give for types is that when you're working on a early code base, we'll have integers, they were numbers, right? We can have strings, they were characters. We can have true or false values, that is Boolean. All those are different types. And those types affect how you compute. So when I give it integers and I tell you to add, you're going to get a different result from when I give you 3 strings and tell you to add them. So types really govern a lot of what we do. And also, there are languages that have strong typing. How many of us have interacted with C++ or Java? Just make a show of hands. You realize as you define a variable in C++ or in Java, you have to specify the type. Like integer x is equals to 5. You have to specify the type. So some languages are strongly typed, others are weakly typed. Like we don't have to specify the type, we just assign a variable to that. If you assign a value to that variable and it defines the type. So if I say x is equals to Charles, Charles becomes the variable and it becomes a string now. If they say x is equals to 10, what does it become? A number or an integer. So Dream have state. State is a memory. It's what makes software temporal and is what might become. So the best way to put it is without states, computer programs will only be mathematical calculations. Think of it from this aspect. The moment you create an account, let's say on Instagram, and we log in to Instagram, do you realize that your feed tailors to who you really are or based on your profile? If you go to make a payment, maybe on an e-commerce platform, we'll realize that some information from a different section about you pops up. Welcome back, Charles. Welcome back, Jay. So that information is determined by states because somewhere with the computer program, there is a memory that saves that information. And that is what makes computer programs work. And that's what differentiates them from mathematics, just doing 5 times 5 to get 25. For us, for those of us who are in web development, we've checked something to do with state management and some libraries to do with state management. For React, what do you use for state management? Someone? Redux toolkit. For Vue.js, what do we use for state management? Anyone? Have you heard of RxJS? Okay, MVRX for Angular. Let me start there. Julia. So when you're busy editing, at some point you'll have to control states because states is memory and it's what makes your program reliable in its design. In any field, we'll have to rely on some states. Even in security, we'll have to rely on some states. And then finally, you need proof. We need to know if I put 2 numbers, let's say it's a simple calculator, and I'm adding 1 million multiplied by 70. How do I know that the output is correct? I need to prove it. And I have to prove it with simpler numbers, whose outputs are already known. For example, if I test a program that takes in 2 numbers and gives us an output, and I give it 2 and 2 and it gives me 4, then I have proof that if I give it bigger numbers, I'm getting the right answer. So what is where proof falls into? And then abstraction. I get into abstraction. I think this is the best slide to show abstraction. So if we understand code, this is the best way to look at it. But if code is still familiar to you, is still kind of strange to you, the best way to explain abstraction in a car. If you look at a car and the driver is sitting in the steering wheel, what does the driver say? The steering wheel and the pedals. But a car itself is an abstraction in real life because no one is actually explaining to the driver there is an engine with pistons that have to fire using a certain sequence and the engine revs up. If drivers had to understand how an engine works and how the gear shifts, then how many people actually use the car? Very few people. And at the beginning, that's how computers were like. not everyone could use a computer because you had to be that machine assembly language programmer or machine code writer with punch cards to use a computer. But right now, abstraction is what makes us with these softwares. An operating system itself abstracts a lot of things from the complexity of your computer. So a good example here is what a web request looks like in the background. So as a developer, we use this XHR is the library behind making these requests in the browser. But I want you to look at this code and compare it to this code. Those two codes perform the same function. We are all getting a request from a certain API. But if you look at what is inside two, it's way less and simpler compared to what is in the first slide. But both of them are doing the same thing. So sometimes when you're writing your software, you need to abstract it in a way that it's easier to understand, it's easier to maintain as a developer. And even when it comes to VI UX, you need to abstract some operations in a way that they are very easy for the users of your system so that no one has trouble interacting with software. So that is a good show of abstraction because these Axios under the hood, Axios uses XHR. So we still be used, but it has been abstracted behind what Axios.get. That itself is abstraction. So you're hiding complexity from the users. And that is where you might fail most of the time because you find that most of the softwares are hard to interact with. How many of us have interacted with a platform that had a lot of buttons and navigations that confused us? And you are wondering, how do I get to just sign up? I just want to sign up. I want to see my profile picture here. I don't know why they're asking all these questions. And if designers and developers decide on such aspects, then your product becomes hard to use. Not bad, not dysfunctional, but it becomes difficult to use or operate. So let me just get back to this composition, combining parts to form wholes. This is what makes programming and apps. This is what makes building an apps. How you compose. I did example. If we give me a guitar and you give a musician a guitar, what is the difference? We'll have the guitar, same quality, same price, same color, same timing on this stage. That's what differentiates we call them guitarist, a musician, an expert, and a programmer who just has a guitar in their hands. It's how they compose. How you put parts together in your solution is what makes your solution an art to begin with. So composition is the art of combining parts in a very conducive manner to suit the solution that you're trying to come up with. So a good example is if I have an e-commerce, I need to links the payment part perfectly. I need to bring the user management part perfectly. I need to bring the order part perfectly. They need to compose in a way that it works. And these disciplines apply across all those scopes. So same discipline you use in building a web solution, a mobile solution, if you're implementing anything in cybersecurity, if you're implementing anything in data science, how you compose those parts, how you move from this library to the next, how you build data pipelines for your AI model relies on these concepts. Nothing different. It's the same principles that are being applied differently. And then failure, ability to fail. Failure is a reality. Systems fail. Systems go down. People lose data. But we need to account for that in software. And just remember, it's all under the atoms of what comprises of the art of software engineering. So we need to rethink software development. And even as we rethink it, we need to look at every of these aspects from a realistic perspective. So I want you to imagine you are in a restaurant and you order food. You are two of you work in a restaurant. One of you orders chicken, the other one orders water. Which order should arrive first? In real life, let's not overthink. Real life, water, right? That's how operations also apply in computing. So if you make a heavy request to a backend server from your app, and another user makes a simple request, the bigger request is going to take more time than the simpler request. And you're going to see feedback arrive very fast for the simpler request that is going to delay for the bigger request. So when you are in systems in the real world, we account for that. How many of us have seen error 404? Error 500. That's a failure, but they have captured it to fail gracefully, to catch exceptions. In code, we've interacted with try-catch. Try-catch finally. Python, we had excepts, right? Not really good in all the other Rust languages, but for the languages that I'm conversant with, we'll come across try-catch, try-except, finally. We have to capture failure in a system. And then I'll tie it to time. I give an example with you ordering food from a restaurant. It takes time. But how many of us have gone to restaurants where you are told, as you prepare your order, enjoy the biscuits? How many of us have been in such places? Exactly. DSLs do the same. So as they're fetching your order, other operations are happening. And as you're waiting, something is happening. Concurrency. Async. An asynchronous operation is an operation that allows you to wait in the process. So I've ordered chicken. The person I've sent to the kitchen to check whatever is chicken has to come back and confirm, oh, we're preparing it. I don't expect them to come without the chicken if it's ready. They bring back the chicken. So every time you think of an API in net development, think of a waiter in a restaurant who've requested a meal frame, and you have to get to the back end, which is the kitchen, get the tail end, which is the food, and find it on your table, which is the front end. That is the best way to understand APIs. And it's never going to be confusing. So the operation of waiting, them, leads to be asynchronous. That's why in your code you write async, await, because you have to wait for the response. That's why you find some words like promise. Someone has promised you, I'll boom the chicken. It's not there. It's a promise. But until it arrives, it's when it becomes now the actual chicken that you're waiting for. So your payload arrives and depends on time. Time itself has affected a lot of things, including distributed systems. There is a definition earlier that stated that a distributed system is a system that can fail because another computer somewhere has failed. How many of us have had such a definition of a distributed system? A good example of a distributed system is all the applications that we use nowadays. They are distributed systems. If you log into a social media platform like X and there's no feed showing up, and then someone says servers down. So because the servers are down, the X in your phone is not working. It's a distributed system. And he's placed in the background. Time, failure, abstraction, all this in any product you can ever think of. Anytime you ever think of software development, software engineering, look at that canvas. That's everything. It's all captured there. Everything. Every step. Syntax is covered in types and states and computations and proofs. Failure handling is covered in failure. Distributed system data is covered in time. And abstraction is what makes it usable. And if you combine abstraction and composition in a very good way, that's an art. So I'll just give you a very simple proof. It might have not been covered in any of the lectures any of us went to campus, that it's something that we should know of. The word computer or compute comes from mathematics, right? And I first started with a question, is software engineering a science, mathematics, an art? Where is it? So I want us to look at this, something they call carry-forward correspondence. And it's a remarkable observation that there is a direct structural identity between mathematical proofs and computer programs. So if you write any formula and you're trying to prove a concept, the same methods that you use to prove that concept are the same methods that are used to run a computer program. Okay, let's look at it from this angle. In a mathematical way, we can propose something. You can say, let X. We used to do linear algebra and algebra, that maths back in high school. I think high school, right? Or campus. We used to say, let X is equals to Z, right? So that is mathematics. In computer programs, you say const X is equals to 5. That's the same thing. Proof. We need to prove something. That piece of code that executes 1 plus 1 to give you a 2 is a proof. Assumption. We need to assume something in maths. Let's assume X, let's assume pi is equal to this number. So in computer programs, we have variables that we assume. We say, let X be anything. That's why you have any types in TypeScript. And then we need to imply something. A implies B. So in programming, that's a function. It takes in an input and gives an output. A conjunction of B is like saying multiplication in computer programs. Disjunction is like using a sum pipe. False, that's Billiam. So all these can be mapped. Mathematics and programming is mostly the same thing. And why are we looking at maths? Why are you looking at all this? I wanted to think of a problem in real life. Anytime we walk to a client, then give me a story. I have a business. I had users. I would like to register. I would like to make it easier for my customers to get reports or invoices of what they did buy from my shop. That's a problem, right? In words, from a person in the market. Another way we can look at it, I'm trying to look for another problem. A good example. You walk into, let's say, a library, like Beyond, and they tell you, we have walk-ins, but you like to track who has borrowed which book. That's a problem. It's a story. How do you convert a story, break it down, and build a solution from that story and deploy a system that is being used? And like that is not enough, generate a result of it. And that's why it's important to understand how to look at concepts from different perspectives, because that's into the vision of, let's create first a database for books. Let's first create a function that adds users to the library, a function that varies books, a function that does X, Y. So we need to build solutions from scratch. But sometimes it's very hard to convert that idea, a art tale, to a product. And you wonder, those who beat, are they magicians? No, they aren't. We just follow the concepts and we did stuff. So be a good example of an implication. We are implying at this point, at this point, we are implying that provided you give me a name, and then it's give you a string. So if I say brute Cynthia, it's always going to give me an output that hello Cynthia. So this is an implication in NANDs. But in software, this is how it comes out to be. So I mentioned this earlier about typesys. There are programs that will compile types at runtime, others at execution time. That's why when you're writing code in, let's say, Java, it's going to be different from JavaScript, because Java is going to give you bugs from the beginning. So as we almost signed up, we've seen what software engineering comprises of. We've heard of the term project, product, system. But what is the difference between the three? Oh, I'm using on this project, or we are building this product. There's this system. What differentiates the three? So a project, think of it as a day defines process. It's not real time. Build of a website, that's a project. It's delivered in a certain time on a budget and to spec. So that's what a project would be like. It's temporary. It has a defined start, scope. Most of our school projects, we are building our projects. So you started, you had a team, you finished. That's a project. Then we have a product. A good example of a product is what you interact with on a daily basis. That is software tools like VS Code, Figma. So a product is an ordained artifact that delivers continuous value. So the main display here is product management. And this is what you really deal with when you have a solution in the industry that someone is using. That's a product. If you build an app for e-commerce and people are able to put online, that's a product. So a system is the end product. It revolves around how different parts relate. Think of a government health system. It's at some point has to go and check other ministries and departments and correlate that data. So it's an ecosystem mostly, and success is defined by how resilient or adaptive the software system is to the industry. So why all this matters is because most of us treat everything as a project. Even products, we treat them as a project. And sometimes you miss out on very important aspects of all this. Because you treat everything as a project, continuity, adaptability is going to be left out. So it's not because most important software systems, the most important software is systems. Not because of individual features, but because of how those parts interact, evolve, and adapt. And that concept there is very important when you're building something. So think of yourself as someone who will come up with a solution or guide a whole team of engineers. If we're given engineers, we asked, what problem are you facing? Oh, you like a software that checks in this and that. And then we're given 50 engineers, well-schooled and well-skilled. Are you able to deliver it? So your ability to digest this is what is going to matter at the end of the day. So we'll look at what kind of activity programming really is, and we look at it from very different angles of people who looked at it. Some of them looked at programming as a federal system. That's why you have languages that look like maths. That's why you have functional built-in languages. So Dijkstra viewed programming as a strict mathematical discipline and rejected software engineering. So some of what the system has looked at is like maths based on what you do. Others looked at it as in a scientific way, as physical simulation governed by limits of compute, that is CPUs and GPUs. So we hypothesize, come up with ideas, write code, we experiment, test that code, we observe, see what it does, and we revise it, we improve it from time to time. So Dijkstra and John were conflicting because Dijkstra was looking at it as a ephemeral system, and John Carmichael was looking at it as from a case of a scientific, from an experimental angle. It's important to look at this because when you understand what software engineering really entails, building a product will never become an issue because you can know what type of paradigm to use for what context. Some systems would be good when you use object-oriented approaches. Others would be better when you use functional approaches. And softwares that would interact with the bank system that you use to pay and receive money works differently from that social media platform. It's very important so that you can work across diverse platforms. So finally, you can see others looked at it as a discipline construction. Margaret Hamilton coined the word software engineering. Before, it was not known as software engineering. So programming as a life-critical discipline where code errors have fatal consequences. So at the beginning of code, people were not organized. They were just building solutions that at some point, the systems that were depending on these solutions were really critical, like health, security. So we needed to formalize how we do software. And that's why we have software engineering principles to date. That's why we come up with models of software development, life cycle, agile. All this was coined because of some consequences that people faced in the past. So she's also one of the pioneers who was being called for very important space program, the US, took people to the moon. So Linus, of course, Linus argues that programming is a matter of good taste because superior logic doesn't handle edge cases. Looks at it as an art. How do you express software? I also like looking at software as an art. He writes spaghetti code that is entangled and confusing. It's going to be a problem for people to comprehend what he really meant. So software, always remember that you need to use a lot of time to maintain it than write it. So you need to write it in a well-organized way. So it's an art because it applies knowledge to the web. And of course, you require to be skilled to write a program. And you need to produce something beautiful. When you like the products that we use, someone sat down, thought of an idea, and they created a game. And we can play that game in a metallic box, and the game simulates a real world. Is it that or not? Look at it that way. That's what we mean by objects of beauty. So part of this shows how it has been evolving from time to time. We started with Ada Lovelace, algorithms, Turing Universal Machine of 1936. At 1945 to 1960, we have now programming, machine code. Then he lived to higher level languages. In 1968, we have software crisis. That's where software engineering is coined. We need to be organized. We need to have a discipline to do this. In 1970s, people now start competing. Is Java superior to C++? Is functional superior to object-oriented? But time still moves them. We get to 1991, internet comes up. And this triggers something big. Because now from the internet, we have open source. Because now people can collaborate and build the real internet, right? And of course, you have to scale because I can work from anywhere. Then, in case something else happens, the mobile phone, that changes the ecosystem that software is run. Not only the personal computers but our phones, different devices. And then, right now, we are all talking about AI, LLMs, and what a new problem, vibe coding. So vibe coding is an issue because there is a discipline to the software that you write, and you've looked at code as mathematical proofs. You need to understand what you're doing. You need to understand the operations that you're coming up with. But if you don't understand and you're writing code for the sake of writing, then that's what vibe coding is. And you can't vibe code other people's money, right? Would you have vibe coded bank platform? So I was launching an e-commerce, or not, a fintech solution, and I was like, I sat down over land on a Saturday, and they coded this. You need to put your money in a coded project. So it's very important to look at it from a big angle. So when we are talking about AI LLMs, remember that these systems run on code. Code is written to deliver that pipeline. That model is code. And they're following the same principles of writing code. Data science follow the same principles. And you're not going to write Python notebooks just for the sake of Pioneer notebooks. There are principles. And for us to build scalable solutions and leverage AI in a good way and LLMs in a good way, we need to be disciplined how we do it. So at its best, it's one of the most intellectually serious activities a person can undertake because this intersects maths, language, design, and ethics, and system theory. So you're doing computations, yet you have to talk to people. There are languages that we are using to program, of course. Then to design, there are ethical constraints. You just can't design a software that spies on people. And of course, you need to understand how systems work in real life. If people visit supermarkets during the day, then your system should support that. You can't build a system that works at night only for an operation that works during the day in real life. So let's do it differently. Most of us might mistake the instrument for the music, but we need to learn the instrument and play the music. So when you have a hobby, the big other way around. So yeah, mistaking the instrument for the music. But you need to learn that skill. You need to learn that art and then play that music. And that's what makes you unique in the industry. So we need to write stuff like you mean it and build it like it matters. Someone here is working on a sales squad that was to take people to moon. That is, we were human lives, right? Do you think they miscalculate positioning? And they're not working with GPS. You're working with some other positioning in space. Are you going to miscalculate that? If your friend mentioned to you that I have built this life support machine, could you use it? And someone you know. Do you trust your friends for such? Why? So you need to build some stuff. You need to build things like they matter. And from that angle, we can now think of serving stuff that is affecting communities, taking it to the market, and generating revenue out of it. And you can now stop watching stuff from the screens and experience them in real life. When we talk about programming in real life, writing code, how many of us will show up to this stage with a laptop, an empty Visual Studio Code, and build a simple solution within an hour when everyone is watching? Not in YouTube. How many of us can do it in real life? Walk into this city, identify a problem, distract it from engineering perspectives, and come up with a solution. Think of systems theory. Systems theory, there are different systems. If you start looking at it from an angle of, you see, this is web development, this is mobile development, this is AI, and view it as a whole system. An AI system runs on a website, which is built and web, right? We need security. That's in the security. We need to analyze here as data. That is data science. So all these are different domains, but they interrelate. But when we make mistakes of cutting this domain separately and limiting ourselves, then we limit the solutions that we can build and place them outside here in the industry. So principles are not limited. Principles span all over. So the same principles that we use in web are the same principles used in data science, are the same principles used in mobile development. Look at it from the instrument perspective, and you can play any music, be it in cybersecurity, be it in development, web, mobile, AI, data science. We can build meaningful solutions. And this was the purpose of our first session, to rethink software development and to have continuous sessions that we do really stuff. We talk about code from a perspective we can look at. We utilize tools. We're in AI, right? Most of us use the same AI tools to come up with solutions. But have you asked yourself this question? If AI was so efficient for any normal users to come up with a software, then you could well be millionaires in AI. Because I just wake up tomorrow and spin products every morning. I just wake up and spin products to the end and make money out of them. But because it's an art and it leads you to be good at what you're doing, we have to learn it. We have to approach it in a structured way and come up with outputs, solutions that mean something out here in the industry. So at this point, I would welcome any questions. This we've had in dissected on a lot of stuff, but I like to also respond based on the questions so that I don't speak my mind alone, but also express feedback. Thank you.